So good morning. Today we are going to discuss about binary search tree. So what is binary search tree means? It is nothing but it is an ordered binary tree. Is a variant of binary tree in which the nodes are arranged in order. So whenever the nodes are arranged in order, that is called as a binary search tree. So in binary search tree, all the nodes in the left subtree have the value lesser than that of the root node. And correspondingly all the nodes in the right subtree have the value either greater or equal to the root node. So if you go for what is root node, it is a special type of node that is called the root node. A special type of node is called as a root node. So it is the topmost node that is present in the binary search tree. So whenever you compare with that root node, the value should be lesser, means you have to place it in the left subtree. If the value is greater than the root node, then the value should be placed in the right subtree. So this rule is applicable to all the subtrees in a tree. So due to the efficiency in searching elements, binary search tree are widely used in dictionary problems. So where the codes always inserted and searches the element that are indexed by some key value. So this is known as a binary search tree. So this binary search tree make the efficiency in searching the elements. So that's why we are using this binary search tree. And this is a simple example of binary search tree. 39 is the root node and 27 is the left subtree and 45 is the right subtree of the node. So if you compare all the values that is present to the left side of the root node is the value that is less than the root node. So 39, if you check the left subtree, all the values should be less than the 39 root node. And if you take 45, 54, 59, so these are the values that are greater than the root node. So right side, all the nodes are greater than the root node. So this is the simple example for binary search tree. So here comes the some values are given. So using this value, we are going to create a simple binary search tree. So 45, 39, 56, 12, 34, 78, 32, 10, 89, 54 and 67. So these are the values given. Using this value, we are going to create a binary search tree. So 45 is the root node and I'm going to insert 45. So 45 is inserted after the 39. So you compare 45 with 39 and 39 is lesser than 45. So you insert at the left side. So similarly 56, you compare 45 with 56. 56 is greater. So it should be placed in the right side of the root node. Similarly 12. So you compare with 45, it is lesser. Then you go for left subtree and 39. 39 compared with 12, it is lesser. So place it at the left side of the 39. So 14, 5. Next is 34. You compare with 45 and it is lesser. So compare with 39. 34 is lesser and compare with 12. So if you compare 12 with 34, 34 is greater. So you place it on the right side. So next, similarly goes on. So next one is 78. You compare with root node, it is greater. So place it on the right side. And 32. So 32 is lesser. So you place it in the left side of the 45 value. So you compare with 39, 12, 34. After that, you place it below 34 at the left side. So next one is 10. So you place it below 12. So similarly, if you take 89, it is greater than 45. So you compare with 45, 56, 78. So if you are going to compare with 78, you have to place the value at the right side of the 78. Then the value is 54 and 67. So you have to place it at the right side of 45. So below 56, at the left side you have to place 54, and if you take 67 below 78, you have to place it as the left side of 78, since 67 is less than 78. So in this way you are going to create a binary search value. So now we are going to check the searching a value in a binary search tree. So the search function is to check whether the given value is present in the tree or not. So first you have to check if the binary search tree is empty. So if it is empty, you can't able to check the values. If it is not empty, then the value you are searching for is present or not will be displayed using the algorithm. So if there is nodes in the tree, then the search function check to see if the key value of the current node is equal to the value to be searched. So if not, it check if the value to be searched for is less than the value of the root node, in this case it should be recursively called on the left side of the child node. In the case the value is greater than the value of the node, it should recursively called on the right child node. So in this way you are going to check the values. So here comes the algorithm for searching the value in binary search tree. If you take a search element is a function tree comma value with the parameters. First step, you are going to check if tree data is equal to value or tree is equal to null, then return tree. Else, if the value is less than tree data, then return the value that is searching for the element that is present in left side. So tree of left comma value. Else return search element tree of right comma value. So in this way you are going to search the element. So first of all you are going to search if tree data is equal to value or tree is equal to null. Then return tree. If the value is less than the tree data, you have to check for left side, or else you have to check for right side. So next one is algorithm to insert a value in the binary search tree. So you have to insert the element using this algorithm. So you call the function insert tree comma value. If tree is equal to null, then allocate memory for tree. Then set tree data is equal to value. Then set tree left is equal to tree right is equal to null. Or else, if value less than tree data, you have to insert the value at the tree of left value. Or else, you can insert the values at the tree of right value. So you check for null condition, whether the tree is null, allocate the memory for a tree, or you check the value that is less than tree data, then you can insert the value at the left side of the tree. Else you can insert the values at the right side of the tree. In this way the algorithm works. So next one, we are going to delete the value from binary search tree. So the delete function deletes the node from binary search tree. So we have to go check with the properties of binary search tree that should not be get violated. since the nodes are not lost in the process. So the deletion of the node involves three cases. The first case is deleting the node that has no children. For example, deleting the node, that is, if you take 78, it has no children. You can also delete 55, it has no children. So similarly, in this way, you have to delete. So if you're going to delete a node that has no children, then the tree remains same. There is no, it will not affect any other nodes in the tree. For example, 78. So you check with 45. 45. So 45 is the root node, and 78 is greater. So go for right side and compare with 56. So 56 is lesser than 78. So you go and check for right side, and 78 is there. So you delete the node 78. So in this diagram, you can see that there is no changes in the, it does not affect any values in the binary search tree. So this is the case 1, and next one is case 2. So deleting a node with one child, that is either left or right child. So to handle the deletion, the node's child is said to be the child of the node's parent. Now, if the node was the left child of its parent, the node's child becomes the left child of the node's parent. So correspondingly, if the node was the right child of its parent, the node's child becomes the right child of the parent's node's parent. So if you take 54, so it has only one child, that is 55. So now I'm going to delete 54. So if you check with 54, so 45 with 54, it is greater. So go for the right side, and 56 compare with 54. So 54 is lesser, so go for left side, and this 54 should be deleted. So you can replace the child of either 55 with the 54. So you are deleted. So this is the second case, and third case. So deleting the node with two children. So we are going to delete the node with two children. So to handle this case of deletion, replace the node's value with its in-order predecessor, that is the largest value in the left subtree, or in the in-order successor, smallest value in the right subtree. So the in-order predecessor or successor can be deleted using any of the above cases. So 45. If you take 56, so 56, it has two children in the left side and it has two children in the right side. So 45 is compared with 56, it is greater. So go to the right side of this root node and check. If I remove the 56, I can place 55 in that particular place, or else I can also place 78 in the place of 56, because it is a in-order predecessor and in-order successor. So in these two cases, you can either place the largest value in the left subtree, or you can place the smallest value in the right subtree. So this is the deletion process. So here comes the algorithm for deleting the value from binary search tree. So you call the function delete tree comma value. If tree is equal to null, then write the value not found in the tree. Else if value less than tree data, then delete tree of left comma value. Else if value greater than tree data, delete the right tree of right, comma value. Elif tree left and tree right. You are going to set the temp as equal to find largest node of tree left. So now you set tree data as equal to temporary data. Now delete tree left, comma temp data. Else set temp is equal to tree. If tree left is equal to null and tree right is equal to null, set tree is equal to null. Else if tree left not equal to null, set tree is equal to tree of left. Else set tree is equal to tree of null, right. So you are going to end the if condition. You can free the temporary value. You can end the if condition. So in this manner, this algorithm works. So next one is that determining the height of the binary search tree. So I'm going to determine the height. So you can calculate the height of the left and right subtree. Whichever height is greater, one is added to it. Since the height of the right subtree is greater than the height of the left subtree, the height of the tree is given as equal to height of left subtree plus 1. So if you see this diagram, you can see that left side you have got 1 value and right side you have got 3 nodes. So 2 plus 1 is equal to 3. So this is the height of the binary search tree. So this is the algorithm for this one. So you create a height of tree. If tree is equal to null, then return 0. Else you set tree height is equal to height of tree left. So you can set left height is equal to height of tree left. Set right height is equal to height of tree right. If left height greater than right height, so return the left height plus 1. Else return right height plus 1. So you can end the if condition. In this way, the height of the binary search tree is found. So next one is determining the number of nodes. So to calculate the total number of elements or nodes in binary search tree, we will count the number of nodes in the left subtree and right subtree. So number of nodes is equal to, given by the formula, total nodes left subtree plus total nodes right subtree plus 1. So same, using this formula, we are going to create an algorithm. So total nodes is equal, total nodes, we have to call the function total nodes parameter tree. So if tree is equal to null, then return 0, else return total nodes of tree left plus total nodes of tree right plus 1. So in this way, this algorithm works. So simply you add the total nodes that is present in left subtree plus total nodes present in right subtree plus 1. That becomes the total number of nodes. So next one, deleting the binary search tree. So I'm going to delete entire binary search tree from the memory. So we first delete the elements in the left subtree and then we can delete the elements in the right subtree. So delete trees is a function called a tree. So if tree not equal to null, then delete tree of tree left, then delete tree of tree right. So you can free the tree. So in this way, you can delete the complete binary tree or full binary tree or entire binary tree. So the last one is that finding the smallest node in binary search tree. So the basic property of binary search tree states that the smaller value will occur in the left subtree. If the left subtree is null, then the value of the root node will be smallest as compared with the nodes in the right subtree. So to find the nodes with the largest value, we will find the value of the leftmost node of the left subtree. However, if the left subtree is empty, then we will find the value of the root node. So this is here comes the algorithm, find smallest element of is a function and with the parameter tree. If tree is equal to null or tree of left is equal to null, then return tree. Else, return the find the smallest element. This is the function name. So it will return the tree left. So this is the end of the algorithm. So in this way, you can find the smallest node in the binary search tree that is present at the left side of the left subtree. So these are the things we have learned in this session. So what is binary search tree, how it is inserted, how it is searched, how it is deleted, and what is the height, what is the number of nodes present, how we are going to delete the entire binary search tree, and how will you find the smallest nodes in binary search tree. So thank you.